Well, for my next big project, I've decided to dive in and actually design and build a valve-based guitar amplifier from scratch. Well, not really from scratch. I'm starting out with 3 solid-state amps, which I'm going to salvage for parts as much as I can. Let's see how this goes. Before I get started, I really should ask myself the simple question, why am I building a valve-based guitar amp? I don't even play guitar or, matter of fact, any other instrument. I don't even listen to much music that needs an amp. I'm not really friends with any band or any musicians. The only relationship I've ever had with the music industry is with my late elder brother. He was a very accomplished guitar player who could play anything from jazz, blues, to hard ripping heavy metal, to classical guitar pieces. Well, like most family dynamics, I at best ignored his talent and at worst mocked him for it. Finally, I've really only been working with electronics for about a year now, so I might be biting off more than I could chew. Well, the only reason I could come up with is that it's going to be a very good learning experience. Contrary to what most musicians think, the valve amplifier is probably one of the easiest circuits to build. You could build one with as little as 3 resistors, 3 capacitors, 1 valve, an output transformer, and a small speaker. Now, it might sound like crap and have no volume, as well as being quite dangerous, but it will still be a valve amplifier. So the question comes back to why build from scratch? You can just go out and get a kit. Well, it would be fun to put a kit together, but I'm not really going to learn anything. All that's going to happen is I will confirm that I can't read and follow directions very well. As well, they're not very cheap. I've seen them go from anywhere from $800 to $2,000 to $3,000 a pop. I'd rather buy myself a new oscilloscope than shell out for a kit that expensive. Well, someone also suggested to me that I run out and buy myself some sort of classic valve amp and restore or rebuild that. Well, let's see. I have a little less than 0 amp experience, a little more valve experience, and practically no electronics experience. Knowing the way that some people feel about classic amps, I really don't want to end up on the next episode of D-Lab's The Cobbler. A classic amp is going to set me back a lot in coin anyway. Even a one in relic condition can be quite expensive, and replacement parts such as the transformer can be very dear indeed. Well, I could also just build one up from a schematic, but to me I wouldn't really be learning much. It's much like a kit. I'm just following along, not knowing why I'm hooking resistor X to pin 9. I'd much rather learn what the function of the different components are than just where they go. For me, I'm the sort of person that really has to know why a component was selected and its function in a circuit. Building any design from scratch is much easier than one would think. You just have to follow the engineering approach. The first step is to define what is to be built. The second step, spec out those definitions. The third step, block out the design. The fourth step, test and evaluate the various blocks. The fifth step, make changes as required. And finally, build out the design to the final specification. Now, to go into a little more detail, the definition stage is when you do all your research. Now, there's about 120 years worth of valve experience out there in the world, and about 99% of it can be found on the web. I'm also a member of the Vintage Radio Club. If I ever have any questions, I just ask. Those old guys love it. You can also find full course materials on valve electronics, as well as a large number of old electronics textbooks. There are also a large number of websites that go into absolute minute detail on how to build a valve amplifier. There are also many hundreds of online forums out there that you could go to and ask questions. For example, one question I had to ask for this project was what's the sort of standard output of the pickups on a guitar? Once you've done all your research, it's time to spec out your design. Basically, you figure out what goes in, what is supposed to come out, and then you choose the basic components they're going to fill in the middle. Blocking out the design is next, and that's the simple process of breaking your project down into the smallest functional blocks. From this abstract block design, you can zoom into each block and start building a schematic for each, selecting components that best match the specification you worked out in the last step. Now that you've blocked out the design and have a preliminary schematic, it's time to test those various blocks in the real world. How you test out your schematic is up to you. I myself use a pegboard. Modern-day breadboards can also be used. You can buy and even make for yourself specialized prototyping circuit boards for valve work. The important part isn't how you actually do the breadboarding. The important part is that you actually do it, and any changes you make while prototyping, you incorporate back into the schematic. Now that you've done all your testing, it's time to build out your design. The first part of the build out is to do a mock-up of your design, either digitally or physically, so you can actually test to see if you can fit all the electronic components into the chassis. Once you've got it all worked out on the mock-up, now it's time to actually go out to drill your holes and build the design up, hopefully not making too many changes as you go along. So let's start the design process by defining our end goal, which is to build a small practice valve amp. I want an output of between 1 and 2 watts maximum in a small chassis, say 50 centimeters on one side, with a moderate speaker of about 4 ohms or less. It should also weigh less than 10 kilograms. And I want to utilize components I have in hand. For those components that I have to buy, I plan to use only those that are in production and available. I also plan to reuse as many components as possible from my stash of used and abused transistor-based amplifiers. So now that I know what I'm going to build, or at least have a general outline of what I'm going to build, let's zero in and start part 2 of my definitions, which I'm going to call input and control. Well, first, I want to have the input voltage supply 120 volts and 60 hertz. So it's basically just stuck here for North America. Next, I want to define my input signal size. Now, I did a little research for this and found out a value between 100 and 300 millivolts should cover almost 90% of all guitars. We need some way to get the guitar signal into the amplifier, so we need an input jack. And we defined our project as a practice amp, and because of this, we should add in a second input jack. This allows for either a microphone, another instrument, or another line input to be played at the same time as the guitar. Next, we'll need some sort of volume control, and finally some sort of tone control. And that rounds out the input and control definitions. Now that we've got the higher level definitions all worked out, it's time to start drilling down into some of the details. So let's start with the power supply. Of course, the first thing we want is a transformer. This isolates us from the mains voltage. Believe me, the last thing I want to create is something with a hot chassis. Now, given that I want to keep my costs down on this amp, do I really need a whopping big transformer with a 312 and 6 volt tap? These weigh anywhere from 3 to 6 kilograms and can cost anywhere from $150 to well over $600 for a super deluxe model. So what I want is a 1 to 2 kilogram power transformer in the $50 range. I also want it center tapped, as that gives us more options in creating power supplies. We don't need a heater tap. We need at least a 300 milliamp rating, and I would like to see a little step-up voltage gain on my transformer. For the power supply, we also have to look at what comes before the transformer. Now, of course, I want a 3-pronged plug for safety, and I want a double throw switch, again for safety. When this type of switch is off, both the neutral and hot are fully disconnected from the mains. Finally, I want to add in a fuse, and I want to put this on the line side before the switch. Again, another small safety feature. For the next part of the power supply, we're going to look at rectification. We basically need some way to take our AC voltage and convert it into DC. Our choices are either modern diodes or some combination of valves. Contrary to popular belief, there is no magic in valve rectification. True, on really big powerful amps you can get something called sag, but we're not building one of these. So I think in my case, I'm just going to stick with silicone diodes. This will keep my design simpler and a little cheaper, as I have one less valve to worry about. Even at this early stage, I'm about 99% sure I'm going to use a diode bridge in my design. Now that we've got some of the power supply details worked out, let's look at the input parameters. Now we know that we're looking at a 100 to 300 millivolt input signal. Now that signal is just too low for a power valve to amplify to drive the speaker. So we're going to need some sort of preamp so we can boost that signal up to a level where the power tube can drive a speaker. Now I also want a tone control and a volume control on my amp. Now the problem is, with my rather small input signal, I can't put the tone control before the preamp. I have to put it after the preamp. And if I do that, I don't have room for the volume control. So that requires me to add in a second stage amp. So now I have my tone control following the preamp, my volume control following the second stage, and then my power stage. So now that I got the signal input all squared away, let's have a quick look at the signal output. First, I have to define some sort of output topology for my guitar rack. Once I've got that all sorted out, I will have to pick some sort of audio transformer that matches the chosen topology. Finally, I'll have to pick some sort of speaker that matches the overall topology of the output stage.
Options for amplifier topology are kind of limited in the valve world. You basically only have 4: A, B, AB, and C. We don't really have to worry about C because that's really just for radio frequency applications, not something we're going to be doing with a guitar amplifier. There are many books out there on the subject. I'm not going to go into too much detail. I'm just going to put up a few graphs to try to get the basic concept across. So let's start with your basic graph, and on the left-hand side we'll plot grid volts, and on the vertical axis we'll plot plate current. When you plot these two values for any valve, you get what is called a characteristic curve, or an operating curve. I just plotted an imaginary one here for an example. Now in any valve, you've also got another important point, and it's this line here. It's called the cutoff line. Now for this particular example, the cutoff is at -4. Now for any signal that's coming onto the grid that is above -4 volts, current will flow across the plate. For any signal that's coming in that's below -4 volts, current will not flow. So let's now graph an amplifier running in Class A. First, we have to set the bias of the valve, or to use another term, the operating point. Here we've set it at -2. Now any signal coming into the valve will fluctuate around this bias line. Now if we put a 1 volt signal through this valve, we will never go up below cutoff. So there's always current flowing through the plate. Amplification always occurs on a linear portion of the curve. Now on a Class B amplifier, the bias point is set at or near cutoff, so that when a signal comes into the valve, for half of the cycle of that signal, there is no plate current flowing. You also might notice that amplification is happening at the very near and far ends of the characteristic curve, which means the signal will be distorted in some way. Now on a Class AB amplifier, the bias point is set somewhat above cutoff, but below the midway point. So when a signal comes into that class of amplifier, current is flowing 1/2 the time for some of the time. As you can also see, this signal will also be amplified mostly undistorted. Each class of amplifier has its advantages and disadvantages. Class A, there is little or no distortion, but there's not a lot of amplification, and it's not very efficient. Class B gives you lots of amplification, but there is some distortion. On the good side, it is much more efficient than a Class A amplifier. Now on Class AB, you get more amplification, some but not as much distortion as in a Class B, and it's a little more efficient than Class A. The main disadvantage of AB is the circuit design is much more complex than A and B.
Now before I select my amp topology, let's have a quick review of what we want in this amp. Well, first, we're not putting out a lot of watts. As well, we don't care about power consumption, as we're not going to be battery powered or running off of some form of generator. As I've stated before, I want a pretty simple circuit. I want a good sound and with little distortion, and I want to save money on valves. And if I could have just one single output valve, that would be perfect. So given all this, about the only choice I have left for amp topology is a Class A amplifier. Now that I've got the output topology all worked out, I can select what sort of audio transformer I will be needing. Well, I know it can be single-ended. I'll need a tap most likely for 4 ohms or less, and I'd like to keep the cost under $40. Finally, we get to the speaker. Well, with the size of my amp, I'll need about an 8-inch speaker, and with the topology I've chosen for the amplifier, the impedance of the speaker should be 4 ohms or less. So that rounds out the definition stage of my build. I really have enough to go on now to start writing the specifications. I could also start doing a preliminary block diagram and even a preliminary schematic. But I think I've rambled enough for one video. Stay tuned for part 2, where I'm going to tackle the specifications. And if I'm lucky, we'll get some of the block diagram done.
Hey Riley, we've been really lazy this summer, not doing any projects, at least radio projects, and not doing any videos together. Maybe we'll start changing that now that fall's here. I can see that you're getting really enthusiastic for the rest of my projects. And well, talk to you later, Riley. See you down in the lab.